Hello, everyone. Welcome to Tier 1 Intervention Podcast, talking about strengthening the Tier 1 core classroom with academic and non-academic interventions, strategies, and techniques to meet the needs of all students, regardless of ability or disability. I am jonily and I am here with my partner in education, partner in crime, Cheri Daughter.
Hey, everybody. It is great to be here. I'm Cheri Daughter.
All numbers can be represented by shape. If we do nothing else in our math classrooms, that is to be deliberate and intentional about seeing number as shape. Making rectangles is one way to do that. Rectangles are the least complex as far as classifications, properties, characteristics. Rectangles are much more basic. So to use rectangles to represent number first is a good foundation for students. Today, we're going to focus on the rectangle and how powerful the rectangle can be for giving students access to mathematics. And also, most importantly, and I haven't said this yet, improving number sense. If we can improve students' number sense, we also open up access to all other levels of mathematics. The more multisensory experiences and engagements we give kids associating math, number, and notation with shape, and specifically today with rectangles, the more the memory is going to increase of those experiences. As I go through the progression of making rectangles today, many students will have difficulties making rectangles and tracing on grid paper, following lines on grid paper. And once we can get them to master that, then they will start to see number and shape as a connection, improving their number sense. I'm going to walk us through the first interaction of making rectangles with kids. Each of these Tier 1 math intervention sessions is structured the exact same way. Aside from seeing number as shape, the other most important exercise we can have kids do to improve their sense of numbers is counting. The two things I talk to primary teachers about, if you do nothing else, do these two things. It's counting and number as shape. At the secondary level, the more complex counting and numbers, seeing number as shape, is also going to continue to increase students' number sense and continue to increase their connections and associations with higher level mathematics. When I introduce this situation for the first time, I might spend 6 minutes on it. I might spend 10 minutes. I might spend 40 minutes. Time is relative depending on your comfort level of this task, but also the level of engagement of students. Making rectangles is closely related to 120 chart. Once you have the initial introduction and the initial process, then we're going to repeat the process over time, maybe once a month with our students. And yes, we're going to increase complexity each time, but more often than not, we're actually going to just repeat the process with a different number over time. To introduce making rectangles, I just want to use my favorite 3 words. I want students to tell me about rectangles. Tell me about rectangles. And oftentimes students will say there's a long side and a short side. There's 4 sides. They might say it's a parallelogram. It's a quadrilateral, 4 right angles. But I want to increase the complexity of my questioning and prompting. That is going to give more substance for student thinking, reasoning, and sense making. Whenever we're delivering these Tier 1 math intervention tasks, our focus should be thinking, reasoning, and sense making, and not answer getting and solving. Answer getting and solving will be an outcome. Fluency and automaticity will be an outcome. But the input is going to be me prompting to facilitate thinking, reasoning, and sense making. It's through thinking, reasoning, and sense making that students are going to retain the information because they have an opportunity to process it. So my first question is, how are rectangles and squares different? And how are rectangles and squares the same? And at this point, I might do a turn and talk. I could do this with all of you, but I'm not going to take the time to do it. A good instructional practice would be to have students pair up, talk to each other in pairs about how rectangles and squares are different, and how rectangles and squares are the same. Then after they pair up in pairs, each pair can get with a small group of 4 or 5. After doing that, pairing for 2 minutes, grouping for 2 minutes, that's given students 4 minutes of processing time. It's also given them an opportunity to move. They have to physically move their body to face their partner, or they have to turn their chair around to face the people behind them. They have to do the talking now. So the auditory, they're going to hear someone else's voice, but they're also going to be speaking their voice. These turn and talk techniques based on these instructional prompts are going to give kids sensation and sensory experiences that are going to allow them to process the information, which is going to create deep learning. Not only deep learning, but also focus and engagement at the current present time. And we're not going to talk about the mathematics as much about how squares and rectangles are the same and different. We'll do that with our kids, but I want to be very specific about the instructional techniques that allow students to feel these sensations, which are going to lift learning, give access to learning. Now, friends, combine that with the visual. Let's just continue to bring in all of these sensory components. It'll get more visual as we go, but right now I'm going to show you the number 24. And what I'm going to ask students to do is tell me about 24. Again, I could do a turn and talk, allow that processing. A lot of times I might just have kids shout out at this point. When we do too much turn and talk, it's not as novel. One of the biggest motivation and focus factors and engagement factors for students is novelty, which is one of the reasons I'm not going to do a 2-week unit on making rectangles. If I'm doing making rectangles for 2 weeks every day, it loses its novelty. I don't have the space in between the interactions. I have taken this really intense, rich mathematical experience and I have flattened it because I haven't had the space in between. The purpose of every one of these 12 tasks and all 12 of these tier 1 intervention sessions that we're presenting is that we present the task once and let time go by, 2 weeks, 1 week, 3 weeks, 2 months, before we bring the task back again.
It's time to hop on into the classroom and join jonily as she talks to 6th grade in this Hear Me Teach segment of the podcast.
This is grade 6, but it's exactly what we did in grade 8. And we might take it to different levels, so that's fine. But we are in grade 6, and in your folders, you have that packet, which I'm calling the square packet. Okay, you can take that out, but we're going to start with something else, but I want to refer to this. Make sure your name is on this, so if it gets out of your folder or whatever, you've got it. The reason this is the square packet is because we are investigating squares and side length of squares, as well as what are some of the other math concepts that go with squares and side length of squares. We talked about this last week. LMA?
Square has 490 degrees.
Perfect. What math symbols and notation and stuff, though, come out of it? Lauren?
You could do with squares, you could do multiplication.
Okay, hold on. I'm not asking it right. I'm not asking it, but I'll take what you said about multiplication, okay? How do we write in mathematics repeated multiplication? Like 5 times 5 times 5 times 5 times 5 times 5 times. How do we write repeated multiplication, Charlie? Exponents. And then what's the opposite of an exponent of 2? Because an exponent of 2 means a number squared, Jack?
A number multiplied times itself.
Yes. So a number multiplied times itself gets you a perfect square number. How do I undo a perfect square number? Theo? Square root. Okay, you guys are pretty well versed in this, and I'm very happy with that. Okay, as we're looking at these tilted squares, okay, we went into a deep mathematical trench last week. I don't even know if we've survived it, okay? But we went really deep and intense last week into side lengths of squares and square roots and steepnesses of lines and fractions with numerator 0, fractions with denominator 0. We went way crazy lunatic, okay? We're going to back up today and we're going to focus on one part of the square, which is the side length. So you're going to get a new geoboard sheet, and these are only going to be lengths of sides. Now, these lengths of sides are a length of a side of a square. We could extend this and make squares out of all these. We're not going to worry about that today. We're only going to look at these line segments. The line segments have a length, like how long is it? And that's what we've been doing. We've been saying, okay, well, let me ask this. If the area of a square is 16, what's the side length? Tell me on 3. 1, 2, 3. Oh, hey, you're not with me. But listen again. Re-trigger. If a square has area 16, what's the side length? Tell me on 3. 1, 2, 3. 4. Best wrong answer? 8. Okay, good, you're back. All right. The square root of 16 is, tell me? 4, not 8. Okay. The length of the side of a square compares to its area. So if I know the area, I can square root the area and find the side length. So all of you, and this was LMA, this was your question last week, but wait a minute. How can the name of this line segment, how can the name of this side have different names? It does, because it has a length. It has how long it is. That's a measurement. The length might be 2.76384. But it also has a distance, and it also has a steepness. Everybody give me a horizontal line with your arm. Horizontal line. What is the steepness? 0. Very good. Vertical line. What is the steepness?
Undetermined.
Undetermined, undefined.
Impossible.
Okay, impossible. Now, then you have these varying degrees of steepness. How do we measure steepness of a line segment? I don't know if you'll remember this, but that is what we're going to focus on. Lauren, how do we measure the steepness of a line segment? The slope. This is great. I wasn't even expecting that word. That is really mathy. But what is the steepness? How do we find the steepness or the slope? Ryan? Yes. How do we find the steepness or a slope in non-math words? What words did I use to say, okay, here's how we give the direction of the steepness? What words did we use? Oh, I know others don't know. But I want you to think about this. What words did we use? Oh, you already got, sorry. On this new paper, put your name. Yeah. Oh, sorry. Okay. Go ahead and go to, let's say, number 5. Find number 5 on this. And look at the bottom dot. If you need to look here, look up here. Look at this dot. Look at this dot on number 5. If you gave me directions on how to get from that dot to the top dot, how do you give me directions for steepness? Yes. Boom. There you go. Okay? So we start here and you tell me how much you go up and how much you go over. Now, you could go up or down and you could go right or left, just like when we were graphing our pumpkins and our leaves and things like that on the coordinate plane. LMA.
I just made this mistake. I don't know if it's the same or not.
That's okay. Go ahead.
So for number 5,
Yeah.
I went up and over, but I went over and up.
It's okay.
That's still equal to the same.
It's going to be the same number, but it's going to be the same two numbers, but it's not going to be the same one number. And let me tell you, and sometimes it will. Because when we do an up over, we're creating a ratio, a fraction. So on number 5, how much up do we go? We go up 2, and how much over? Whoops, I'm under 5. You also go over 2, okay? The up or down, the down or up, is always the numerator. So LMA, the up or down, the vertical distance, the vertical up or down is always the numerator. Okay. And the left or right is always the denominator. That horizontal movement is always the denominator. Just like on a coordinate plane when you're graphing ordered pairs, like our leaves and pumpkins, we actually do the left or right first, and that's the first number in your ordered pair. So this is mathematically defined this way. Now, what is the steepness then? Look at 2 over 2. Oh, good. Look at this. Oh, Caleb, good. Good focus. Anthony, McGuire, Stevie, Emma. What is the steepness if I have a 2 per 2? Caleb?
1.
Boom. Good for you. This has a steepness of 1 because that value is 1. Now, if this were a 3 over 2, that would give me a different value if I wrote it 2 over 3. So that's where we have to be careful that the up or down goes. Okay, so your job right now is to find the steepness, the up and over, the fraction of each line, not the length.
How do you figure out?
That's a great question. Don't even worry about it today. Ooh, yes. Best wrong answer is 8. But no, that's the best wrong answer.
Oh.
But I love it. You guys are thinking today. This is great. Now, your steepness has to be written as a fraction. It's a ratio.
Would it be 7.5?
Ooh, I love it. Love it. You can leave it at that. That's beautiful.
Basically, a half plus a half would be 1, right? Or...
Yes, but you would do a half times a half.
Oh, yeah.
Because you're doing 7.5 times 7.5. A half of a half is how much?
1/4.
Good, yeah. Good. Okay, so you're finding the steepness of each of these line segments and you write it as a fraction. So if you guys go to number 3 here, I'm at this dot. How much do I go up to get level with the next dot? 3. And how much over? 1. So I write that as a fraction, 3 over 1. 3 per 1, 3 over 1. The steepness of number 3 is 3 over 1. That's how you write it. Yeah.
Would this be negative?
It would be. Ryan has a great point. Some of these steepnesses are going to be positive and some are going to be negative. And you can tell by looking at it. What is this one, positive or negative? Yes, it's very intuitive, so that's great, Jonah.
Would this be negative 5 over 1?
And it wouldn't be 5 because if you go down, you got to count the spaces. 1, 2, 3, 4. 5 dots, but 4 spaces. So it would be negative 4 over 1. Negative 4 per 1. Yep. Huh? Okay, start here. And how much do you have to go up to get even with that dot?
1.
So from this dot to this dot is how much?
0.
0. To here is 1. And here is 2. So you go up 2 and over 1. And you write that as a fraction. 2 per 1. 2 over 1. Yeah, girl.
Notice each time we make it, it looks like a triangle.
Beautiful. That is going to be so essential, important. Yes. How are we doing here?
Good.
Okay. So how steep is this, though?
1 over 1.
Oh, is that a 1 over 1? What is that?
That's it means it's negative.
Oh, but it's not a negative slope.
But what if this is on the left side?
No, look, it's going upward to the right. All 3 of these top ones are positive slopes. Okay? It's positive, but I have to know what it is. Give me the fraction that it is also. Yeah. Yeah.
I'm just having trouble understanding.
You're fine. You're totally fine. Let's start at this dot. You want to give me directions from this dot to this dot in terms of ups and overs. So we start here. How much do we go up to get even with that dot?
2.
2 and over? 1. The steepness of this line is a 2 per 1. 2 over 1. The steepness is a fraction. So 2 over 1 is your result of that. I'll be right over, Caleb. Good. Now, is this going to be a positive slope or a negative? Positive steepness or negative? It's going upward to the right. That's going to be a positive. All 3 of these are going to have a positive steepness. Which one would have a negative steepness? No, but this one's a tricky one. This one would have a negative steepness for sure. How we doing? You're fine. You're going to go from this dot to this dot. So how much do you go up? How much is, what length is that to go up even with this dot? No, it's 3 dots. But from this dot to this dot is 0. That's a length of 1, 2. You go up 2 and over how many? 3. So your answer is a fraction up per over. So up 2 over 3, so 2 per 3, 2 over 3.
Wait.
So your steepness is described as a fraction.
So is it 2/4?
Oh, no. How much did you go up? You went up a length of 2, and you went over 1, 2, 3. Yeah.
So is it 2/3?
2 over 3. Yeah, 2/3. Yep.
This is easier.
Huh?
25.
25 is best wrong answer.
No,
Nope.
25.
It's not 25 because what you're doing is what's the square root of 16? Let's go to this one.
Because that's what I got, but then she said it was wrong.
Yeah, what's the square root of 16? If you have a square, yes, it's 4. What's the best wrong answer for square root of 16? 12 is a popular one, but 8 is a more popular. But the correct answer, square root of 16 is
32.
no.
So it would be 8. Wait.
Stop. Stop.
Wait, so it would be, it's 100.
No, best wrong answer is 8.
156.
No, you're going the wrong way. Think the other way. If I have a square pizza and it has 16 pieces, there's 16 unit squares. The area is 16. What's the side length?
8.
8 times 8 is not 16, 64. The square root is, yes. Square root of 16 is,
Oh, wait, yeah, that's what
you
I
had
meant.
that,
The
yep.
square root of 50 would just be 10.
No, because what's 10 by 10? 10 by 10 gives you what?
125.
100. So square root of 50, best wrong answer is 25. Because a 25 by 25 is not going to give you 50 squares inside. That's the tricky one.
15 is so hard. But then what's 16?
We don't have anything yet. Huh?
How do we do this one?
This is great. Let's go from this dot to this dot. How much do you go up or down? 0 per, how many do you go over?
3.
So what's your fraction?
3 over,
No, 0 over 3 is your fraction. 0 over 3, yes. That is beautiful. That is beautiful. Love it. Yes. There's nothing for that.
There's nothing?
Nope, nope, nope. Nope, it's totally good. McGuire. Are we 2 o'clock or 2:15 today, Miss Pence? 2:15. Okay, perfect.
How would I do this one?
Ah, this is good. If we start here.
2 over 0.
No, because here we can't go up, we have to go down. How much do we go down? 2. So it's going to be a -2 per, how much do I go over? 1. -2 per 1. -2 over 1. Yep.
If there's one like this, you can't go up on it, right?
You could if you started here.
Oh, yeah.
Then you could go up 2, so that's a +2 over, you go left 1, that's a -1. I'm going to write this, McGuire. +2 over -1 is equal to -2 over +1. You could write it either way. They get the same result. Yeah. I'm so sorry. Yes.
So it depends on what dot you start on, if it's positive or negative.
It does, but it won't change the ultimate result. Go ahead.
But I've done all of these.
Yes.
All of them were positive for me.
Okay. By looking at the line, you can tell which ones are positive because they're going to go.
So if it's this way, it's positive.
It's positive.
If it's
Yes.
This way, it's negative.
So let's look at this one. If I start at this dot, I'm going to go up 4, which is a positive 4, and
then
left
negative
1. Yes. So that would be 4 over negative 1. Or if I start at this dot, I go down 4 and right 1. So that would be negative 4 over positive 1.
So
Both
the
of
ones
those
that
results are
lead-
the same.
All the ones that lead this way, should I just pick one?
Yes, because positive 4 over negative 1 is going to give you the same overall result as negative 4 over positive 1. Yeah.
This before
Yes. What's the best wrong answer?
8.
Good.
And with this one, that's either 10 or 5. Because 5 is
Ooh. Okay. Here's the thing. It's neither one because if it's 10, what's 10 times 10? Remember, it has to be the same. And 5 times 5. Best wrong answer because 25 times 25 is a whole lot more than 50. You need 2 numbers. There you go. And Liliana, the whats have to be.
I know.
Yeah.
It's not going to be a whole number.
It's not going to be a whole number, but it will be a positive. Yeah.
I don't know what my
Yeah.
brain was thinking. This 64 perimeter of 64, do you just do 64 times 2? Or 64 times 64? It's a square root of 64.
Okay. First thing, draw a square that has area 64. What can you tell me about that square? If you have a square pizza and there's 64 pieces inside, what can you tell me about that? The side length is 8. There is one. There is, because what's the square root of 64? Oh, there isn't one for 50. Hold on. 8. But 8 is the side length, but this says, oh, but wait a minute, you need to find the perimeter.
7 times 7 perimeter is 8.
Side length is 8.
Because that's
If-
the same thing.
No, don't whine.
8, 8, 8, 8.
Yes.
Because this one.
So what's the perimeter? 8. Perimeter is the outline. And if you have 8 4 times, the perimeter would be, which is,
So there's not one because 8 times 8 is 64, 7 times 7 is 49.
you are beautiful. What I might say is, yep. So what I might say is it's between 7 and 8. Is it closer to 7 or closer to 8?
Closer to 7.
Closer to 7. Now I'm going to do this one with everybody after I meet with Stevie. Hold on, because I'm going to bring everybody together in a moment. Oh, don't whine.
I'm stuck on 15. It has to be
Okay.
a decimal. I
Yes.
think it's
Which one are you doing?
15.
Oh, good. This is what I'm bringing everybody together for.
I think it could be 0.
It's not 0. And it's actually more than 5. Because what's 5 times 5?
6? No, 6 is 30.
6. It's more than 6.
Yeah, but it's
Awesome. What's up? Oh, okay. That's what we're coming together. All right. Come together in 4, 3, 2, 1. Psst. Okay. Re-trigger, refocus. Actually, you guys were like really engaged on this today. It must have been like at a just right level for you. I must not have pushed you hard enough. I'm sorry. You're welcome. This was too just right today. It was too just right because you guys were fully independent. Now we're going to shake it up a little bit, okay? Now, I want you to go down to the bottom and look at the square root of 16. What is the best wrong answer? Tell me. 8. I think I've talked to all of you about this because I think I've said it 16 times. What is the square root of 16? Tell me. 4. Okay. Square root of 16 is 4 because what this means is 4 squared, or in other words, 4 times 4 is 16. Meaning if I have a square pizza that has 16 pieces, the side length is 4. That's all that means. The square root is not in our standards. You have to master it by 8th grade, but it doesn't show up till 8th grade. So to me, it doesn't make sense. If you have to know square root by 8th grade, but you don't start learning it till 8th grade, it's just not good, okay? So we want to get some exposure to square root now, and that's all that it means. Square root of 16 is 4 because 4 times 4 is going to give us 16. Now we want to look at this one together. Square root of 50. You guys are on the right track. Best wrong answer, tell me. 5 and 10, but a better 25, okay? Wrong answer, 25. Because if you tell me 25, what you're telling me is you have a square that has a side length of 25 by 25. Already in one row, you've got 25. In 2 rows, you've got 50. In 3 rows, you've got 75. We're already past 50. Now, the square root of 50, as you guys have been telling me, stay with me, okay, is between the square root of 49 and the square root of 64. And you guys rationalize through this really perfectly. What is the square root of 49? Tell me. 7. Square root of 64? 8. Now, okay, let me ask this. Raise your hand for this one. Raise your hand to tell me a good guess for square root of 50. And don't say 7.5. Caleb.
5.
Say it again.
5.
No, it's going to be between 7 and 8. Kendall? No, don't say 7.5. Okay, Kendall, thank you. Now, no, it's not because... What? For what? What is it?
There is none because it's closer to 7. But there is.
Hold on.
7 times 7 is 49. 8 times 8 is 60.
Yep.
9 times 9 is 81.
Now,
Decimals.
okay, hold on. You're actually all right, but we're not gonna conclude that today. Okay. Psst. Front row. Re-trigger here. Okay. Square root of 50, Caleb. The reason I didn't want you to say 7.5 is because you would be telling me that 50 is halfway between 49 and 64. What's 50 closer to? 49. It's way, way closer to 49. Now, what Kendall said was, you know what? Hey. What Kendall said was, you know what? I know it's going to be less than 7.5, so I'm going to say 7 1/4. The issue is, we said 7 1/4 in 8th grade. I'm going to tell you 7 1/4 is too big. So what I'm going to do is, as you are guessing these, you're going to try to make the numbers simpler to compute. Now, I want everybody to turn your paper over to the back, your steepness paper. Turn it over to the back. Okay. All right. We're going to note take this, and you're going to do some solving. Okay? I don't want your opinions right now, so put your hands down. We're going to note take this. We know that it's not 7.5. So on the back of your page, put a number 1, and I want you to write 7.5 times 7.5. We know that's not going to get us to 50. Is it going to get us to more than 50 or less than 50?
Less. Wait, more.
Okay, here's the first thing you're going to do. Everybody draw a square and separate it unequally such that you put your 7.5 separate, 7 1/2. That's number 1 on the back. Don't do it now. Don't do it now because you're going to miss the next example. You're on the back of that one. Hey, your steepness, you're on the back. Come on. Okay. Number 2, the second one you're going to do is, I like what Kendall said. She's, you know what? I know it's going to be closer to 50. It's going to be closer to the 7. So let's try 7 1/4 times 7 1/4. And again, I want you to set up your generic rectangle here unequally. 7, separate your 7 and your 1/4. Then do a number 3, and this is what we ended up concluding to in 8th grade. We said, you know what? Maybe finding half of 7 is okay, we can do that, but 1/4 of 7 gets a little bit sticky. I'm going to already tell you that 7 1/4 times 7 1/4 does not give you 50, and it's going to be too big. It's going to be a lot bigger than 50. So what we said in 8th grade today is, to make the computation simple without a calculator, we are going to say a number less than 7 1/4 that's easy to compute. Don't worry about why, but we said let's try 7 and 1/7 times 7 and 1/7. Then you're going to draw your square, separate it unequally, split up your 7 and your 1/7. And what you are going to do now is you are going to do all 3 of these computations and get an answer. Go ahead, and I'm going to start back in the corner with Stevie. You're going to do all 3 of these computations. Yes, ma'am.
Could it be 7 and 1/16?
It absolutely could be. But if I was going to do 7 and 1/16, I'd actually do 7 and 1/14 because it's an easier mental computation. Don't worry about why, just know that. If we did a number 4 example, I would actually do 7 and a 14th times 7 and a 14th. But yes, your logic is right for 7 and a 16th, but then I would have to find a 16th of 7. And for me, mentally, it's much easier to find a 14th of 7. And that may not make sense, but just trust me for now. Okay, so you're going to do all these computations. So you're going to figure out all these computations. Excellent. That's a really great organized note-taking, Mira. Good. Good, yeah. What is it? 1/2 times 1/2. 1/2 of 1/2 of 1/2.
1/4.
Do you agree with him? Yeah.
Wait, so does that mean 1/4, 1/7? I think I know how to find it. So you just need a number times a number that equals
What's half of 7?
1. A number times a number that equals 1. So I think it is 7.001.
Okay. Great. Write that down. You don't need to calculate it, but write that down.
Is it 3.5?
Yes, it is. Yes, it is. Liliana, you are like on fire.
How would I do this?
Same thing. This is actually a 1/2 of 7 also. It's the same one. Yes.
Okay, so you times those 2 first.
Yep, and that's going to go in this box. So what?
Those 2.
Yep, and then these 2 is going to go here. And then this one is going to be how much is a 1/2 of 7.
Are we adding that or times?
Then once you get all 4 numbers, then you add them all up.
How do we find 7 times a half?
What is 1/2 of 7? 1/2 of 7. What's 1/2 of 6?
4.5.
Oh, not 4.5.
3
Sorry.
and a half.
Yes.
Wait.
1/2 of 7 is 3.5. Yes. Which one are you doing here?
Everything.
Okay. So if you do 7.5 times 7.5, what's 7 times 7?
49.
49 goes right there. This says, what is 1/2 of 7? What is 1/2 of 7? Yeah.
Once we get all here, wait. So
What's 1/2 of 7?
3.5.
Good. Yep, that goes there.
yeah,
For what?
If we found all the answers.
when you get
To get the answers, you're going to multiply because you're finding the area of those sections. No. 49 is not your side length. Your side length is 7.5. Yes, 7 times 7 is 49, and then 1/2 times 7 is 3.5. 7 times a half is 3.5, and then what's a 1/2 times a 1/2? 1/4. Now, once you have all those boxes, then you're going to add them all up. 49 plus 3.5 plus 3.5 plus 1/4.
I think it's unrelated, but
No, that's okay.
1/4 times 1/4,
Good girl. What's a 1/4 of a 4th?
1/16.
Yes, girl.
So that's why it wouldn't be 1/8.
Correct. Correct. Good girl. Good. Yes.
so we're trying to add these up, but we have no clue what the decimal of 1/4 is.
Wouldn't it be
Oh, decimal 2.5. Or you could change these to fraction. 3.5, 3.5. How much is 3.5 and 3.5?
3.2?
No,
What
I'm
the
better
heck?
with just or adding decimals.
Yeah.
Okay,
What
fine.
is it?
Yep.
That's what we're learning.
It's going to be 0.25.
Thank you.
You're welcome. Okay, what we got?
I'm really confused.
Wait a minute. I agree 1/4, and I don't agree 1/8. Best wrong answer 1/8. 1/4 of a 4th.
How do I add that?
You could change this to a fraction. What fraction would this be? No. Oh, girl, that's terrible. Wrong answer. Watch. 3.5. 3.5 plus a fourth. Or you could change that to a decimal. What's the decimal for a fourth? How much is a fourth of a dollar? Decimal 25. So then you could do 3.5 plus 0.25. Yes. Oh my gosh, kid. Yeah. Uh-huh.
I just found out 7.1 wasn't the answer for 15.
Oh, okay, wait. Let me make sure you did that procedure correctly. Let me take a picture of this before I forget. Okay. You did 7.1 times 7.1. 7.1 times 7.1. 1 times 1, 1. 1 times 7 is 7. Put your placeholder. Did you do that? You did? And then 7 times 1 is 7. 7 times 7. Did you get that? Okay. And then you did 1, 14, 10, 5. And then because you have 2 places here, you are good. That is beautiful. Is it going to be less than 7.1 or bigger than 7.1?
Big, no, smaller.
Smaller.
But then 7 is 49.
Yes. So what's a number?
1/2.
You want a half of 7. You want a half of 0.1. What's a number between 7 and 7.1?
7.05.
Dang, yes. That was good. Don't worry, Mira. I'm just freaking out. Okay? Oh, yes, sir. Good. And what is, if this is 1/2, what's 1/2 of 7? That's another 3.5. And then what is 1/2 times 1/2? A half of a half. No, a half plus a half is a whole, but a half of a half times a half is 1/4. A half of a half is a 4.
Okay, so would 56 be right?
Oh gosh, no, because that is a half times a half. This box is a half times a half.
What is 7
What's a half
times
of a half? 7 times a half is 3.5.
Yeah.
Yep. But what's a half times a half?
A half times a half.
Yeah, 1/4. 1/4 goes right there. Then when you add all those up, you put the number out here. And friends, back with, oh, yep.
For number 1, it's 24.30.
No. Hey, kids, back in 5, 4, 3, 2, focus. Okay, here we go. Look at this real quick because we have to pack up. Wait. I think you said it wrong, Liliana. No, have a seat. Charlie. Oh, you're, okay, all right. Here, Kinsley. Good. All right. For this number 1, 7 times 7 is 49. 7 times a half is 3.5. 7 times a half is 3.5. What is a half times a half? Tell me. 1/4. Now, if we add all of these up, Kaylin, come on, girl. If we add all these up, 49, 50, 51, 52, 53, 54, 55. Oops, that should be a half. 56 and 1/4 should be the answer to 7.5 times 7.5.
Wait, you were supposed to add them all up? I thought we were adding that, then that.
No, you have an area that is this 4 parts, so you need to add all 4 parts.
So I would have got it right. I just added it.
I'm with you. Okay. All right. All right, kids. Psst. All right. Now, last row. Put your folders away. Everybody put your papers in your folders.
How did you get 56?
I got it because I did 7 times 7 is 49. A half of 7 is 3.5. So 49, 50, 51, 52 and a half. This is going to be another 3.5. So 52 and a half and 3.5. 52, 53, 54, 55, 56. Okay, don't worry. We'll come back.
I tried something new with the glasses.
Oh, good.
You look like the
Third row, fold us away. Yes.
We just wanted to check this here.
Which one?
All of them.
Oh, no, I can't. I have no business.
Mostly this one.
This one is a negative. Oh, no. It's -4/1. Because if you go from this dot to this dot, you go down 4 and over 1. -4/1. Second row, folders away. All right, first row, folders away. They're not paying attention. Grade 6, be with me in 20. Start to regulate yourself, please, in 17. Hey, and I should bring this up because you all know where my classroom is, right?
Yes.
And you guys, when you're across the hall from my classroom, I'm not saying you guys because I know you guys are only half of you. It is a ruckus. It makes me lose my mind. So when you're over there, I want you to fix it, okay? I want you to regulate yourself because it is a hot ruckus over there. If you have not put your folder away, go ahead and do that. I know, Emma, you're finishing. Go ahead, Theo. All right, simmer. Kaylin, turn around. Awesome. Anybody else need to put your folder away? Good deal, good deal.
Mathematical notation comes to life and students understand number better, so they're going to be able to achieve higher. And they're going to have a stronger math fact fluency and automaticity to engage in deeper level mathematics. So thanks everybody for being here. This was Tier 1 Interventions Making Rectangles.